We know the day that Tambora erupted. We know the day that Krakatoa erupted. So we try to find those in the cores to have an absolute age to tie to. So that's one of the important things about these continuous ice core records is that dating. We have dating with uncertainty on the order of 1 to 3 years for the last several hundred years, even extending to thousands of years.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. In the coldest parts of the world, it is possible to dig deep down into glacial ice and collect samples potentially going back millions of years. Ice cores offer researchers a unique opportunity to assess environmental data that has been trapped for many years, broadening our understanding of Earth's system conditions from ice age cycles through to current human impacts. We are joined by glaciologist Peter Neff, assistant professor in the Department of Soil, Water, and Climate at the University of Minnesota. Professor Neff, thank you for joining me today.
Yeah, thanks for having me.
For people that don't know what we're going to be talking about today, what are ice cores and why are they interesting?
Ice cores are core samples that we drill from glaciers all around the world in the polar regions especially, but also high mountain areas. And they're really interesting because in the best case, you can have annual accumulations of snowfall that eventually get compressed into ice that are just like the rings of a tree, and the chemistry of that snow and the impurities in it, and also air bubbles that get trapped in the ice are all different archives of past climate and environmental information that give us really important context, sort of understanding, longer time series of environmental history than we have from our modern observations, and really provide us a lot of really important information.
So the project that brought your work to my attention currently is something called Coldex. Can you tell us what Coldex is or what Coldex is trying to achieve?
Yeah, Coldex is a National Science Foundation Science and Technology Center in the class of 2021, I think, was when we started. And it's a big 15 institution collaboration to try to find the oldest ice core records of past climate in Antarctica specifically, with sort of two goals of sort of using geophysical tools, both from the air and on the ground in Antarctica, to find potential deep drilling sites where we could drill a 1.5 mile deep ice core that would be 1.5 million years old, continuous, like a continuous time series. And at the same time, go to really interesting places on the margin of the ice sheets where old ice is actually brought to the surface by ice flow. So places like the Allen Hills, where a lot of old meteorites are found because of the way the ice flows to the surface. It concentrates old meteorites, but also we're finding that ice is incredibly old and gives us not continuous time series of past climate and environmental information, but snapshots that go way back further in time than the continuous ice core record does, which is only 800,000 years long right now only.
Can you talk about what you're specifically looking for in the ice cores?
Yeah, a whole host of things. So ice is a really nice, clean sort of sampling environment to work with. So rather than sediment cores or tree rings where things can get pretty messy, we in an ice sample can measure just about any chemical element you can think of with all of the various analytical techniques we have these days. So you can measure salts in the ice, which might tell you about variability in storminess or ocean conditions. We measure the isotopes of hydrogen and oxygen in the ice itself, and that can tell us about temperature fluctuations. But I think the most direct and fascinating thing about ice cores, and particularly Antarctic ice cores, is these air bubbles that get trapped inside, which are really just like, if you think of a six-sided snowflake, that there's airspace between those 6 fingers of snowflakes that all pile up in Antarctica. And eventually when they get compressed, that air between the fingers of snowflakes becomes an air bubble that is almost perfectly preserved. So you can get, not a proxy measurement, an estimation of greenhouse gases back in time. You can get a direct observation. Those air bubbles are just little samples of the atmosphere.
Thinking about that trapped air, I know in 2018 or 2019, you had a project where you were melting the ice cores on location to study later. Can you talk a little bit about that process?
Yeah, I mean, the ideal case with ice cores is that we go to Antarctica or the Arctic or a mountain glacier to collect the core and then bring it home to the lab to do our analyses. And do things like put a small ice sample, like ice cube size sample in a vacuum chamber, melt it down or crush it, to then release that old air and bring it into an instrument. But there are some projects the 2018-19 season, I was a postdoctoral researcher at the University of Rochester working with Vas Petrenko on a project he was leading in collaboration with Australia, where we went all the way down to Antarctica. I think we had about 110 days in the field. And because we were measuring a really, really precise thing in the gases, we actually had to melt down and extract that air in Antarctica, and actually at one of the snowiest sites in Antarctica. So if you can imagine, keeping a bunch of scientific equipment running in a snowstorm, and you got to keep your generators from getting clogged with snow. You're getting buried alive in a sort of a shack we had with this 300-liter melting chamber. I called it the hot tub time machine. It was a very clean vacuum chamber that we could put, a couple 100 kilos of ice into, and then melt it down in a big hot water bath to extract that old air so that it wouldn't get contaminated. Get contamination on top of what we were trying to measure. And we were actually trying to measure not just carbon monoxide in that air, but the radiocarbon concentration of carbon monoxide in that air, which is a tracer for how oxidation works in the atmosphere, a really important process that removes greenhouse gases like methane from the atmosphere. So yeah, we go to some pretty wacky lengths to get really high quality samples in Antarctica. So I much prefer just collecting cores in Antarctica. That's hard enough, and then bring them home for the analysis. But of course, shipping a whole bunch of ice from Antarctica all the way back to the United States is also quite an expensive and complicated affair.
Was that logistic aspect of it why it was done on site there for that particular study?
For that particular study, it was just that radiocarbon it accumulates in ice at the surface of the Earth. So once you take your ice core out of the ice sheet, it's no longer shielded from some of the high energy particles that are coming from outer space, these cosmic rays. And that in ice actually produces radiocarbon. But once you remove the air from the ice, you get less of that extra production of radiocarbon. And so that sort of dictated that once the cores were on the surface, they were essentially hot potatoes that were becoming more and more contaminated. So we had to get the air out of the ice. And it was expensive and challenging to get all of the equipment out there to do the gas extractions. But then in the end, you're then shipping home 20 or 30 stainless steel sample canisters that, yes, you have particular needs for how they're shipped, but they're not going to melt. So, but we did have the stipulation with those as well that they actually couldn't go back to the United States on aircraft, because if you take the samples high in the atmosphere, there's again less shielding from these cosmic rays, and so the samples would get more contaminated. So they went all the way back to the States on vessels.
Interesting. So thinking about the ice cores that do make it back to the lab, kind of what's your process once you have them in a controlled environment? Kind of what is the research steps, I guess?
Yeah, right. So there are a couple of phases to the arc of an ice core project. First you find a glacier and a site where you think you can get good annual accumulations of ice. So there's ice core recovery, getting out there with drills, drilling the cores, and then shipping them back to the lab. And then in the lab, there are sort of different specialties in what we would measure. So if you need to do gas analyses, you need to have the right equipment for that, or collaborators for that. And you also have different needs for the temperature of your ice. You can only do that at sites that are very cold, and then you need to keep your cores cold all the way back home. The sort of base suite in cores. So I have two other projects where we're working on reconstructions of the last, say, 200 years. And so then you want annual information over that time. So we're measuring things like the water stable isotopes with laser spectroscopy. We are measuring salts or lead to see contamination in the environment. We also try to measure sulfur compounds, which are going to give you in Antarctica will give you an annual signal in how the ocean freezes over every winter and then melts every summer. But also you get big sulfur peaks from tropical volcanic eruptions, which are in the historical period very well dated. We know the day that Tambora erupted. We know the day that Krakatoa erupted. So we try to find those in the cores to have an absolute age to tie to. So that's one of the important things about these continuous ice core records is that dating. We have dating with uncertainty on the order of 1 to 3 years for the last, several hundred years, even extending to thousands of years. And that's because of that combined, finding annual chemical signals in the core, and then also tying to sulfur peaks from volcanic eruptions. So there's sort of a whole host of things to measure, and it tends to take a village at that stage. We often, one PI will collect the ice core, and then we'll go to the
Right.
U.S. and international ice core community and say, hey, we got this ice. Now I need to partner with a few folks to make all the measurements. And it's just sort of, what stage of the ice core life cycle you're sort of working in. I'm very much in the ice core recovery stage of things in this part of my career. And, now I do have 2 or 3 ice cores of my own that I need to now shepherd through that analysis and then interpretation phase. And I often field work overshadows a lot of the other unseen work that we do in the lab. Yes, we'll spend 100 days in Antarctica collecting samples, but then we'll also spend 100 days in a basement lab, getting our samples just in the right state to then be fully analyzed in a mass spectrometer or laser spectroscope or whatever these, all these whiz bang pieces of equipment we have. So, and then of course as well, right? Once you turn this beautiful ice core sample, we destroy it in the analysis process and it becomes just ones and zeros, just digital data that then, PhD students and postdocs get to have all the fun with it. And then actually interpreting, okay, what do these signals mean? How do they correlate with, climate or environmental variability in the observational period, say the last 40 years? And then once you establish that proxy relationship, you can then push it back in time. And that's where, we get to do this sort of cool time travel with ice cores. If there's a place in Antarctica that's really critical, it's changing fast, like Thwaites Glacier. There's some pictures on the wall behind me of the South Korean icebreaker. We went to Antarctica last December, January, February, and collected some cores near Thwaites Glacier, this really concerning glacier for the future of global sea level. And we have no climate records in that region. So without ice cores, you can be frustrated. Oh gosh, we don't have any, records of climate extending the last 10, 50, 100 years. But thankfully with the ice there and the particular sites we have on the coast, we were able to say, hey, we have an opportunity that, these sites have been recording that climate information for time immemorial, and we just have to go there and collect our core sample.
Is there any one specific thing you would say has been your favorite experience in Antarctica?
I mean, I think the top things are the relationships and the teams that you get to work with. Honestly, like it's a beautiful place to share with people that so few people in the world actually understand. Even with increasing numbers of tourists going down there year after year, there's nothing, you can't really get the experience of living there and working in the place and studying and gaining some understanding of what Antarctica is and how it works and how important it is for the rest of the world. So it's those relationships you get through that intensity that are really a great outcome. But it's the sense of accomplishment as well when projects do come off, and our success rate is fairly high for on ice core drilling projects. And it's just that, once you've been putting your head down for 5, 6, 7 weeks and, to get that drilling target or drill to bedrock, the sense of accomplishment and relief when you do hit a goal. I was on a drilling project for my PhD with the New Zealand Antarctic program where we were drilling 760 meters to bedrock, and you're just charging to get it done and be as efficient as possible. And then once you finally, hit the bedrock, you get to see, the bottom of that part of the Antarctic ice sheet. And then you get that release like, oh, we did it. Never mind the fact that, you've done it, but then you have another month of work to get everything packed up, get back to station, get stuff back to the real world. So it's just an intense place, and it's such a departure from normal life. But yeah, certainly, then getting these samples back as well. We haven't been able to work with the cores that we collected on the Korean vessel yet. It's been almost a year, but, getting funding and equipment in place to do the analyses is difficult. But, for me, knowing the information that's likely contained in those cores and then being able to extract that is super exciting. And particularly that one, because it was my first NSF project as lead PI in Antarctica. And it was, it's really the dream project that I've been pursuing for my whole career. So it's really gratifying to work with folks and have support from the NSF to go do those really wild new ideas.
So one of the other things that you've had some success with is social media, communicating your experiences there. Can you talk a little bit about what that has meant, what difference that has made, what the reactions have been?
Yeah, I've been really lucky to enjoy some pretty wide exposure through TikTok, particularly because of that, that very visual platform and how engaging, Antarctica is on camera. It's a very lucky combination to draw people in with the excitement of going to Antarctica and, sneak some science in at the same time. It's been a really helpful way for me to sort of process some of those aspects of doing Antarctic field work, like that you just can't share with people or people don't get to see. So it's sort of, it's like a portal for the public. Yeah. So social media has been like a great way to help, I guess, socialize Antarctica to a wider public as well and show people what we do down there. I think people have, mixed reactions, but they're, people are pretty surprised at the amount of things we're doing in Antarctica. And you see these big, big pieces of equipment, like big national, Coast Guard icebreaker that comes in to resupply McMurdo every season. Like that ship exists to support the U.S. Antarctic program. That's its one job. And it's really cool to see these things in action. And yeah, it's just that I've been able to give people a really direct view and I've become pretty good, I guess, now over the years of working with the, camera equipment that you need to capture this stuff. Well, like we're very lucky now that the only camera equipment I need is an iPhone that I can keep near my body to keep it warm in Antarctica and then document little pieces of what we're doing, as we're doing it. And, even as I'm leading it, I've sort of been able to figure out how to get just the right, snippets to then be able to show people visually how we get fieldwork done particularly. So, I have a very fieldwork heavy portfolio right now. And so that's what people get to see on social media. And it is more of a challenge to feature, all of the really incredible, detailed, precise lab work that we then need to do to translate that, core sample into scientific information and knowledge for us all to benefit from. But, so trying to keep up the creativity to move as we move through that process and, show then what we do. Like when our cores come back to the States, well, they go to the NSF Ice Core facility in Denver, Colorado. And that's a really fascinating place to go with the camera. See these, core samples that are hundreds of thousands or even millions of years old, the Coldex cores, and be able to, look at them and talk to the curators about them. So, that's sort of the next step for some of these projects.
So the last question I have for you today is thinking about the future and your work in the years ahead. What are you most excited about finding out from those cores you haven't got to look at yet?
Yeah, we really want to understand how the climate in these critical regions of West Antarctica, a place called the Amundsen Sea, is sort of home to the most fast-changing glaciers in Antarctica. And we have really no observational climate information in that region. There are no research stations. It's a really stormy coastline. And so ice cores are the only way for us to get context of the last 100 years or 150 years. And rather than looking at models where we don't really have enough data before the satellite era to say anything concrete, we can imagine all of the trends like, oh, it looks like westerly winds are strengthening in that region. And well, there should be a temperature increase that's observable or that's soon to be observable. But we don't have the records to even observe that and confirm that. I think these ice cores are going to allow us to do that. Man, it's just a really fun, basic exercise of filling in blank spaces on the map as well. We have a lot of ice cores from inland West Antarctica that were collected by NSF projects in the late 1990s, early 2000s. So we have nothing from right out on the coast, right where all of the change is happening. The change in glaciers in Antarctica is largely being forced by the ocean, and the atmosphere also has a role. So we call it ice-ocean atmosphere interactions, super complex three systems interacting, all of which are highly variable in time and in space. And so we need observations. And these ice cores are one in sort of a one tool in the toolkit that we have of, observing the glacier systems now with geophysical tools and getting out there on the ice. But we don't really have a way to gain information about Thwaites Glacier back in time through anything but ice cores, certainly at the resolution that we have. So year by year information, we have a general feeling that some of the retreat of these glaciers was initiated in the 1940s due to a strong El Nino event. I think with these cores, we can, date them back to 1940 and say, well, this is how anomalous temperature was in 1940. This is how anomalous the winds were in 1941 and 1942, and really, firm up that hypothesis of that initiation of this big globally relevant retreat of these glaciers that we're worried is irreversible and could happen faster than is, ideal for society. We know the glaciers are going to continue to change. We don't know, how much sea level rise they're going to be sending our way, and we don't know how fast. So we're really trying to gain better clarity on that. And the ice cores are going to be a great addition in all of the different ways that we're able to do that.
Special thanks to Peter Neff. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.